Hello. In the previous part of this lecture, we discussed about selection of the best subset of variables for modeling, and the conclusion was that while exhaustive search is the best, very often it's very difficult to conduct this because of computational complexity. And recall once again, if we have k variables, it means that using exhaustive search, we have to, without any validation approach, cross-validation approach, you basically running the simplest version of exhaustive search involves estimating 2 to the power of k models, and this is very costly. In many cases, it's not possible. So for this reason, we discuss 2 alternatives, forward and backward selection. And while it is some solution, this solution is not the best, and it doesn't provide, very often it doesn't provide satisfying results, and to this end, we will talk about 2 shrinkage methods today, rigid regression and LASSO, which in most cases it's better than forward or backward selection, and it provides results which are quite close, not very far from potential results of exhaustive search, but in terms of computational efficiency, it's much more efficient. So that's the plan of this part of the lecture. So we're gonna talk about shrinkage methods, LASSO and rigid regression, and how to regularize those models, how to tune those models using cross-validation and cross-validation procedure and validation approach. That's the plan for this this part of this course. So let's start. Today we're gonna use a dataset that you can download from this website. So download this on your computer, then set working directory to the directory where this is downloaded, and before you load this dataset, you will need to use a library called matrix with capital M. And after that, we can load our dataset. Was it data web or web data? Web data. Yes. And now, if we load this dataset, we will have 2 new objects. Y spent. This is a vector Y spent of 10,000 observations, and each row corresponds to 1 user browser. So we have, in this dataset, we will use the browser history of 10,000 people, and our variable that we would like to predict is Y spent, which corresponds to amount of money spent online on this particular browser. So we have 10,000 observations, and we want to predict what are spendings of a particular person, a person with particular browsing history. And here we have matrix, I should say sparse matrix. That's the reason why we loaded matrix. The only difference between standard matrix and sparse matrix is that all zeros, that default value of sparse matrices are in most cases zeros, and if they are not, so if I don't provide exact value for given observation and given column, then I assume that this is 0. Thanks to this, I save a lot of a lot of memory, and yeah. So at this moment, and for this course, you only need to know that if for objects with sparse matrices, dot corresponds to 0. Yeah, and here for this matrix XWeb, which is dimension of 10,000, for 10,000 browsers, we have history of 1,000 most popular websites, and those numbers, for instance, if we take the very first observation, we will have vector of 1,000 elements, but yeah, different people visit different websites, so let's report only those websites that are greater than 0. Yeah. So here this will be vector of true false. Yeah, and I choose only those columns for which was visited by person number 1. So here we have different websites, and this corresponds to percentage points. Yeah, everything should sum to 100, and this corresponds to how often some websites like, I don't know, Slate, Sony Pictures were visited by person number 1. Yeah, and if we sum everything, all those columns, we'll get 100. Yeah, the same thing corresponds to person number 123. Yeah, all websites. So all the time, every time it sums to 100. Yeah, and we have 1,000 potential predictor. Yeah, that depending on frequency of visits of some websites, we want to predict how much money this person with such a browser history spends online. This dataset comes from an amazing, very recent textbook written by Matt Taddy, Business Data Science. Actually, I will put the cover over here. Yeah, and the author of this textbook. Yeah, this textbook was published in 2019, I guess. Yeah, something like this, 2019 or 2018, 2019, and for bachelor level, it may be a bit too advanced. But if you want to get seriously to data science, yeah, you have to buy this textbook. I really recommend this. Yeah, and Matt Teddy, he wrote this textbook for MBA students at Chicago Booth, but then he left the academic career, yeah, and now he's a vice president of Amazon. Yeah, so yeah, and from this book, I know that he knows data science stuff a lot. Yeah. Yeah, so we will. So in this part, we're gonna use this data set. Yeah, most likely this data set is not very recent because many people visit Alta Vista. Yeah, so yeah, nowadays nobody uses Alta Vista, I guess. Yeah, so we're gonna build the model which is the best for predicting online spendings of customers, and notice that this problem is, yeah, from business perspective, is quite relevant, and at the same time, you cannot use exhaustive search, because we would need to consider 2 to the power of 1,000 models. Yeah, so it's not possible for sure. Yeah, and I will show you how to select the best subset of those websites that really matter for predicting online spendings, and yeah, so that's the plan. Also, one additional comment, yeah, that this problem also is nice in this sense that here basically you cannot provide any theory. Yeah, you don't know which websites are important. Yeah, so you explore this problem without any theory. Yeah, so let's start. As you may know from this classical statistics courses, the OLS estimate is a solution to some program. A program which goal function is to minimize residual sum of squares. Yeah, and you can find this program over here. Yeah, and ridge regression essentially has the same goal function, but in addition to this, there is constraint. So this is optimization under constraint, where we assume that sum of all coefficients sum of squared coefficient related to variables. Notice that in this condition, b0 is not included in this constraint, optimization constraint. And in the ridge regression, we minimize residual sum of squares given sum of squared coefficient is smaller or equal to some parameter s. Yeah, so that's that's the main difference from OLS program. And there is also alternative representation of this using Kuhn-Tucker-Lagrange theorem. We can represent the same program of ridge regression using lambda in our goal function. Yeah, and the lower s is, so the more restrictive we are about what betas we can choose, the higher lambda is. Yeah, so there is one-to-one mapping between s and lambda. And in most statistical packages, if we provide parameter for a ridge regression, we provide lambda parameter. Yeah, so this is it. How we can interpret this problem? This problem can be represented by can be illustrated by a situation that we're planning to go for holiday, and unfortunately not now during this lockdown. Yeah, but if we go to some for holiday and we pack our stuff, depending on the size of our briefcase, we will put more or less stuff inside. Yeah, and if our luggage size S gets smaller and smaller, we will start putting only those essential things that we really need. And here the philosophy is very similar. The program, this optimization program, will use in prediction of y, if S gets smaller and smaller, then only those variables that are most important will be included, and those of smaller importance, estimates for those guys will be shrinked towards zero. Yeah, and yeah, that's it. Yeah, so let's see how this works on our dataset. To estimate ridge regression model, we're gonna use a package called glmnet. This package allows us to estimate ridge regression, lasso regression, and elastic net, which is generalization of both model that nests those two models. Yeah, we won't talk about elastic net. We will focus only on those two shrinkage methods, ridge regression and lasso. Yeah, and yeah. So let's load this package, and now if we want to estimate model using GLMnet, it's enough that here we provide matrix of x's, xweb, and our dependent variable. It is y spent. Y spent is in dollars, but to have our estimates of our betas that can be interpreted in terms of percentage impact, let's use this. In on logarithmic scale. Yeah, you should learn this from econometric course. If you don't know how to interpret it, it's not the most important thing from the perspective of this course. Yeah, so but let's use it. This is our variable that we would like to for which we would like to make predictions, and here xweb is this matrix of 1000 potential regressors. Yeah, GLMnet works in this way. Yeah, that if we want to build rich regression model, we have to set parameter alpha to equal to 0. If we want to build LASSO, this alpha parameter is equal to 1. If we want to estimate some combination of those two models, we set alpha somewhere in the middle between 0 and 1. Yeah, but for ridge regression, we set it to 0. Yeah, and then we set lambda equal to be 10. Yeah, and this is it. Yeah, and let's call this ridge model. Yeah, and now as a result, we have a vector of estimates of all those guys for all those 1000 variables. Yeah, the higher lambda is, the higher cost of deviating of betas from 0 is. Yeah, and now if we estimate ridge model 20 with lambda twice as large, let's estimate this, and now we can call coef ridge model 10 will have a vector of all of 1001 coefficients. Why 1001? Because we have also intercept. And if you remember, let's put it this way. Let's print the first 10 coefficients. No, sorry. Here, the very first element is intercept, and few minutes ago I said that intercept is not subject to regularization. Yeah, so if we put infinitely high punishment cost on all parameters except intercept, then we will end up in a model that will provide intercept equal to average y that we want to explain. Yeah. So now, if we compare coefficients, sum of squared coefficients of all except the very first one, if I type here -1, if we type if we type coef ridge -1, we will get rid of the very first element. Yeah, you see that here the first element is 7 to the power of 10 times 10 to the power of minus 5, and it's this coefficient. Yeah, so if we compare sum of squares for model with lambda 10, we will get sum of those squares 2.22. And if we sum squared coefficients for a model with lambda equal to 20 without intercept again, then we will get closer to 0. Yeah, because here it is more costly to set higher values of coefficients. Yeah, so this is it for now. Yeah, so overall, yeah, let's estimate, I don't know, some model high with very large, I don't know, super high with super high lambda. We should get closer and closer to 0. Yeah, here you see. Yeah, it's getting smaller and smaller, but for a rich regression, it's never 0. We will discuss this in a few minutes. Why? Okay. Yeah. So I think that this is it for introduction to rich regression. One of the nice things about package GLMnet is that we can provide many lambdas in one command, and then it will estimate many specifications for us. Yeah, so let's say that we create a grid of something like this. 10 minus 2 and vector of length 100. Then first we will have very high. So here we will have very high lambdas, and then it will decrease up to something very close to 0. Yeah, if we plot this, yeah, those are 100 lambdas that we're gonna provide, and yeah, instead of one number, we provide a grid, and let's call this rich model. Let's wait a bit. Yep, it has been computed, and now what's nice is that rich model here, it estimated 100 models, and for each, actually here it's not so nice, this is better. Yeah, here we get matrix of estimates for different rows are our variables, and columns corresponds to our lambdas. Yeah, so overall, so we have 1001 rows because we have 1001 coefficients because of intercept, and 100 different specification of the models. Yeah, and now what can we plot? Which model? Yeah, this is our rich model, and if we put this as argument of function plot and also provide that on x-axis, we want to have lambda, we will get exactly this. Those here, if lambda notice that here we have log lambda. In one moment I will show you why it is convenient to use logarithmic scale than standard lambda. But here we see that the higher lambda is, those parameters, those coefficients are shrinked towards 0, yeah, and the higher lambda, at some point, those coefficients are getting smaller and smaller, yeah. So now let's make a prediction using GLMnet, but maybe before, what may be a bit for exposition reasons, let's build auxiliary model with only 3 lambdas, yeah, because with 100 lambdas it's hard to show those results, yeah, and let's use those values of lambdas. This is just for illustration, and yep. So here once again, model auxiliary. We have 3 specifications. If we type coef, we will get estimated coefficients. Yeah, there are 1000 parameters. Yeah, but for each lambda we have 1 column. Yeah, and the same thing will be if we use predict and provide here our model, and dataset on which we want to make prediction. Notice that here in standard in other packages that we use, when we use predict, we have for one observation we had only 1 prediction. But right now, because this model, which model contains 3 estimations for each lambda, it provides 3 different predictions for each of those lambdas. Yeah. So if we type dim, we will get a matrix of size 10,000 with 10,000 rows and 3 columns. I guess so. Yeah, this is it. Yes, so now if we want to compute how MSE varies with different lambdas, we can do the following way. That first, we make prediction of our full model, predict rich model on this XWeb. Here we will have matrix with 10,000 rows and 100 columns. Yeah. Okay, and now from this matrix to compute MSE for it. So each column refers to each specification. So from each column we would like to subtract what? Observed values for each individual, for each browser. We can do it there. What I'm doing can be done using function sweep. This function, if you want to yeah, you can read documentation about this here, but let's use it something maybe a bit simpler, I don't know. Yes, so if we can create matrix of our dependent variable. For instance, if we want to create this matrix, the matrix with all those 3 columns the same, we can do it something like this, or Alternatively, we can use function rep and then provide that we want to have 3 columns. Then, you remember, if we create matrix using this function matrix, we enter, if we don't provide this additional argument, we provide all data by columns. Yes, so using this trick, we will get exactly this matrix here, that this is value of log-wise spent for observation number 322, and for 3 columns it's exactly the same. Yeah, and if we want to have as many columns as in our pred, this is 100, it's enough to change this to this. Yeah, so now this is it. Yeah, and you remember the function for MSE. Yeah, you can find this formula below. So we want to subtract, actually, wait a moment. Yeah, for a moment I wasn't sure what should be in the formula. The first, it won't matter because this is squared, yeah, but to be fully consistent with formula, it should be this way. Then we raise to the power of 2. Let's create matrix errors. Okay. Actually, those are errors squared, yeah, but whatever. Yes, so here, for each specification, we have squared error. Yeah, and the dimension of this is again 10,000 times 100. Yeah, and now we are interested. Each specification is 1 column, and now we can use to compute MSE for each specification. We can use essentially MSE on training set. Let's put it this way. We can use function call means. Yeah, so for each column we compute means, and each column refers to one of 100 specifications, so we have MSE train. Yeah, that. Okay, and now if we type MSE train over grid, because you remember grid were our lambdas, we will get, and let's put it line of with these options. If we plot this way, it won't be very informative, because for very wide range of values that we consider, yeah, it doesn't change that much, and it changes a lot if we get closer and closer to lambda equal to 0, where there is we are getting closer and closer to global minimum on training set if lambda is smaller and smaller. Yes, so to make it more illustrative, it is very common to use logarithmic scale. Okay, so now on the logarithmic scale, and here on XLab, let's write log lambda. That will be okay. And now we see that MSE, as the lambda increases, then MSE also decreases. This is not surprising, because this MSE was computed on the training set, and the best model that fits data the best the training data the best is the one with the smallest punishment, with the smallest lambda, which as it gets closer and closer to lambda, as it gets closer to 0, and log lambda is getting smaller and smaller, then MSE on the training set is lower and lower. Yes, so I guess that this is it. This result is that for unconstrained model, MSE is the lowest. Is not very surprising, but yeah, and using the same metaphor with holiday, yeah, our inventory is it cannot be said that it is the most universal for any trip if we evaluate whether this inventory that we packed for this particular trip is useful for this trip. It will be useful, but we should rather evaluate whether those things that we packed for this trip are also good enough for other trips to other places. Yeah. So this is, and by varying the size of our briefcase, it will by reducing the size of our luggage, we will choose things that are more universal for other trips. Yeah, and in this exercise, we will implement the validation approach, just like in previous methods, just to evaluate for which lambda, for which size of this case, we have the best model. Yeah, so this is validation approach. Let's set seed equal to 1. Yep. And now let's split our data set into validation set and training set. Yep. So we have here trained false, and we want to draw number of rows for number of observations, and obviously replacement must be true. Yeah. So we have some allocation to training set and validation set. Yeah, and now in building the model, let's use this. But the only change will be that here we choose only those rows for which train is equal to true, and here we choose only those elements of vector y spent where train is equal to true. Yep. Okay, so now, sorry. Okay, I will run this once again. Lump this, and let's call this this object a bit different. Yep. So now we want to make prediction of our ridge model valid using all other observations. So here I put exclamation mark. Yep. And prediction. Yeah. And to compute MSE on validation set, MS valid, error valid, here we have to choose all those, is it correct? Yep. Those observations that are not in the training set, just like here, and I think that this should be it. Let me check my cheat sheet. Yeah, it looks so. Let's see. Okay, and now if we want to plot this here, plot valid. You see, here we evaluated the model, the different specifications of the model, and the model which provides better prediction on observations that are outside the training set are not equal to, so not all variables are important. So we should drop some of those observations, and the model which mean MSE valid this lambda provides such a cost of including some unnecessary variables that they will be, estimates for them will be very small, and essentially the program, this minimization program won't overfit to our training data set, but will provide more robust model which provides better prediction also on the validation set. So this is it. And also, if we want, we can provide coef rich model. If we provide, after comma we provide number, we will extract only those coefficients for this specification that is the best outside the training set. What is interesting here, notice that here none of those coefficients are equal exactly to 0. Some are very, very small, some are larger, that are important are larger, but none of those are equal to 0. And the reason for this is that this quadratic function, the first derivative of this quadratic function at beta equal to 0 is equal to 0, which can be interpreted as the marginal cost from deviating from this beta equal to 0. If we are at 0, then this marginal cost is nil, there is no this cost here. So always, if I can, I will deviate slightly, just and that's the reason why all those betas are non-exactly equal to 0. And also what is worth mentioning is that essentially if we take MSE train, if we take MSE for on validation set, MSE is larger than on the training set. And it's quite common thing that the model, those data sets the data set that was used for estimation always will exhibit smaller MSE because the model was built to fit this data the best. And on validation, this MSE can be higher. In the previous part, we used the validation approach to determine this parameter lambda, which is the best outside our training set. And just like with other methods that relies on a validation approach, the main concern is that one point is used only for validating or training the model. Yeah, and again, the solution to this is cross-validation approach. And once again, yeah, the illustration for cross-validation approach you can find over there. Yeah, and now we're gonna implement essentially super similar code to the code for best subset selection to cross-validate the parameter lambda. Yeah, and yeah, so let's do it. Let's use tenfold cross-validation, and just like before, we create, we allocate faults where we allocate faults to each. In the other words, we allocate each observation to one of k faults. Yeah, and here it is n row xweb. Yes, some number of observations, and obviously replaced must be true. Yep. But now we have 10,000. Yeah, the length of this is 10,000. As many observations we have. Yeah, and yep. And let's create a grid of our lambdas, and let's use let's use 100 values. Yeah, so this is our grid from the smallest guy is 0.01, and the largest guy is 10 to the power of 10. Yeah? So, yep. Okay. Yeah, so I just read documentation for GLMnet, and it turned out that it is recommended to use sequence which is decreasing, yeah, for lambda. So it's better to have the lowest value at the end and the highest at the very beginning. Okay, so I changed this order, yeah, and now, so that's one thing, and now we want to compute MSE, cross-validated MSE for each fault separately. Yeah, so overall we will create now matrix MSE CV, which will have columns will refer to each specification that we consider. This grid which refers to lambdas, it will be in this matrix. It will be for each column is one of specifications, and each row I, refers to MSE computed on fault I using the model estimated with all observations but fault I. Yeah. So this here we will have k and row equal to k. Okay. And now we create, just like before for best subset selection, we will create for loop, and yeah, we create which model valid, we use GLMnet, and now this is estimation procedure, and we use xweb, only those xweb in iteration I for which faults are different than I, and comma here because this is matrix. Next, this is our our dependent variable, and here also we type exclamation mark equality I without comma because this is a vector, and alpha is equal to 0 because this is alpha is equal to 0 for ridge regression. Yeah. Last but not least, we provide lambda grid, and this is estimation step. And now if we want to, and now we will create prediction for each observation. So this will be 10,000 rows, and for each specification. Each specification is one column, and we will have 100 columns. Yeah. So this is something like this. And now we make those predictions on this fault, which was not used in the estimation procedure. So instead of inequality, we choose those observations. So this is our prediction step. Yeah, and now we would like to compute this squared error for each observation and for each specification, and we can use the trick that I discussed before using validation approach. This will be exactly the same, almost the same. The only difference is that here, yeah, so we create matrix with for which each column is the same, but rows are different. Rows correspond to each observation. The only change that I must do is to change exclamation mark train to false equal to I. Yep. So this is it, and then this error valid will consist. Each column is each specification, each row is each observation, and we want to have the average error in this cross-validation step for each specification. Yes, so if we want to, we want to compute the average squared error, mean squared error for each specification and for fault I. Yeah, and this can be achieved by we take MSE CV, the row that corresponds to fault I, and then we use call means error valid. Yeah. And then, as the result, we should have the matrix MSE CV with each column is one specification, each row is one fault. Yeah. So let's compute this. Oh, it will take a while. And now, as a result, we have matrix of the size of 10 times 100, and if we want to, and now we can depending on MSE CV, depending on lambda, and now again, if we use call means, it will be MSE for each specification. Yeah, for different lambdas. Yeah. Okay. If we plot MSE CV lambda, we will get something like, yeah, we should plot this against grid, and let's use type L. Yeah, this is not very informative. Why? Because it's better to use logarithmic scale. Yeah, that most interesting things happens here for low grids here, so it's better to, yeah. And now we have this. Also, once again, to be very, if we were very puristic, false. If we were very puristic, we should, in computing those call means, we should somehow adjust for different number of observations for each fault, yeah, but results won't be that different, yeah, and yeah. But if you are super puristic, you should rather compute it weighted average with those weights, yeah, here, yeah, but we're not doing this because the results should be super similar. Okay, yes, so now we have this, and our MSE, this, just like with validation approach, yeah, it's the result, if I recall correctly, yeah, it's somehow similar, yeah. And now, if we want to refer to lambda, which is the best, using cross-validation procedure, we can use which. This will return the index of this. This is 81, and if we type lambda, not lambda, but grid, this will be lambda, which generate the lowest cross-validated mean squared error using ridge regression. Yeah, and okay. During this part, always we were using ridge regression. If I said at some point LASSO, I hope that I didn't, yeah, but so far we didn't use LASSO at all. Yeah. Okay, so this is it. Yeah, and okay, so we computed our lambda. Yeah, and now we will do exactly the same thing, but instead of using this loop, yeah, it may be not the nicest way to conduct cross-validation. That being said, yeah, if you do it, yeah, in your data science career, you have to do it at least a few times, yeah, especially for completely new methods, you have to use this all the time. For methods which are super popular, such as ridge regression or LASSO, yeah, you can do it only once to understand what's inside the packages that does this whole cross-validation procedure for you. Yeah, and now we will use package CVGLMnet, which is essentially, yeah, it does exactly what we did using our loop. And so here, that's the name of this command. We provide, just like for standard GLMnet, matrix of variables, our variable that we would like to explain. Alpha is equal to 0 because this is ridge regression, lambda equal to our grid, and let's use tenfold cross-validation. Yeah, n-folds stands for this parameter k that we provide here. Yeah, so let's run this. Yep. Yeah, so now this object, among others, has element called lambda mean, which refers to lambda with the lowest cross-validation error. Yeah, you see, this number is exactly the same number as we had. Yeah, because what we did is exactly cross-validation, tenfold cross-validation, and using this function, it does it for us as well. Yeah. Also, we can plot, and here we have, it refers, yeah, it's essentially the same thing, those red dots. There are standard errors, yeah, that we won't discuss in the topic, yeah, so don't worry about this too much. And there is another criteria that regularizes, that penalize model complexity even more than the standard approach. But also in this course, don't worry about this. Yeah, so in this course, we will use only lambda mean. Yeah, this other lambda it is called lambda one SA. Yeah, one standard deviation. Yeah, so it's mean plus one standard deviation of standard deviation, standard error. Yeah, but it's not for this course. Okay. So now, using cross-validation procedure, we learned that the best lambda that regularizes our estimation procedure is this. Okay, and so using machine learning techniques, we learned the true model in this class of models. Yeah, the model with lambda equal to this. So now, having this information, we can re-estimate this model once again, but using all observations that we have. Yeah, so let's do it right here. Let's call this model reach model final, and we use glmnet xweb log y spent. Don't forget to put alpha equal to 0 because this is a ridge regression, and we could write this way, and then we will estimate only this model with one lambda, but we can also do it this way. Yeah, we estimate this model. Okay, and now if we want to have prediction for our final model using observations xweb and lambda, which is the best for us, here we can, in this predict, we can provide option s equal to, and this corresponds to this parameter lambda that we want to, for which we want to predict. Okay, and this is our prediction. If we type this, we'll have prediction for each specification. Here we chose prediction with the best specification. Okay, and also another thing that we can use using function predict instead of providing the data set, if we type equal to coefficient or coefficients, let me check. Okay, I think that it's coefficients. Yep, coefficients, it works. Yeah, so here we have all estimated coefficients for our best lambda. Okay, and what is quite characteristic for ridge regression is that even though we impose some punishment parameter, tuning parameter lambda, using best subset selection, the selection of the best subset of variables, then we would estimate those parameters only for some observations. And here we see that basically all parameters are different from 0. Why? This is because of quadratic function in this optimization program that you can find over here. This quadratic function, this punishment that we take lambda times sum of squared coefficients, and because of this we impose some punishment on deviating for deviating with betas from 0, but for beta equal to exactly to 0, this marginal cost, this marginal cost of deviating from this is very small, or to be very precise, is equal to 0. And for this reason, there is alternative. So there is something very similar, some very similar function, the optimization program that you can find over here, and some weird websites. Yeah. So here you can find this program for LASSO where quadratic punishment function is replaced with absolute deviation, for which deviation from 0 is strictly greater than 0. Yeah, and you will see how it works, yeah, in the following example. Using GLMnet, estimating LASSO model is super easy. It's super easy. Yeah, so here we have LASSO, we generate this. Everything is the same. The only change is that we replace alpha from 0 to 1. Yeah, if you check the documentation of GLMnet, here you have description of this here, and if we set alpha equal to 1, we will get exactly LASSO regression. Here we're using CV GLMnet. So instead of doing this cross-validation loop that we did with bridge regression, it would be exactly the same for LASSO. Yeah, so let's keep this. Yeah, and let's compute this. Yeah. Okay. Yeah, so we computed this, and now we're interested in the best lambda, LASSO lambda, that was that minimize cross-validation error, and LASSO lambda, that's the guy. Yeah, if we want to, also we could, why not, to plot. Yeah, and here we see that this is, yeah, that's correct, yeah, because this is lambda, and the log of number smaller than 1 is negative. Yeah, so it's over here. Yeah, and now, so now we can LASSO, what was the name of the previous model? Rich model final. Let's use it. LASSO model final. We change alpha from 0 to 1. We estimate this. Okay. And now, if we want to if we want to check coefficients for lambda which minimizes cross-validation mean squared error, we have to type this, type coefficient, and as we will use LASSO lambda. Okay, and now what's in contrast to previous method using rich regression, we see that actually here there are many parameters which are shrinked to 0, so they are not estimated at all. Yes, so if we type so actually we can coefs LASSO, we can do something like this, I guess. Yep. And overall we have 1000 websites, yeah, and here, yeah, coefficients, actually it should be not greater than 0 but different than 0, yeah, because also those coefficients can be negative. Yeah, so we see using LASSO regression we estimate only 232 coefficients, and in LASSO and using rich regression, let's take this coefs ridge, yeah, you see all coefficients, because here we have 1000 variables plus intercept, and none of those are equal to exactly to 0. Yes, so in this sense, if we want to get rid of some variables, then the LASSO is more efficient. That in this sense, it's for us, it selects those variables that are not included in the estimation procedure. For rich regression, always all variables will be included. Yeah, so that's the main difference between the LASSO and rich regression. Yeah, and I think that this is it. This part of the lecture is much longer than I expected. Yeah, so sorry for this. Yeah, but in this part of the lecture we discussed two most commonly used shrinkage methods, ridge regression and LASSO. We discussed how to regularize, how to tune this punishment parameter lambda using validation and cross-validation approach. One problem, one common concern with this type of methods is that this method, this tuning, this method is quite sensitive to units of our predictors. For instance, if we use some values expressed in dollars and assume that, yeah, there is coefficient of some variable x expressed in dollars, coefficient of the impact of this variable would be 1. $1 would affect our y by 1. And now, if we express x instead of dollars, we will express this value in cents, then this coefficient automatically will be 1 times smaller, because our interpretation will be not in dollars, but in cents. And it is a problem, because those whether I express something in dollars or in cents, essentially I provide the same type of information. And good methods should be resistant should be robust to changes in units, and the solution in the family of shrinkage methods, what is commonly used is so-called standardization of predictors, that you can find formula over here, and this procedure relies on dividing our all variables by its standard deviation, and by this all units are expressed in its own standard deviation. So you can say that to some extent it is unitless, yeah, and also is it is much better to use this standardization before we start using those in our machine learning procedures. That being said, actually this is what we were doing before, since the very beginning. Why? Because here we have standardize this parameter, which accounts for standardization of all predictors, and default value is true. Yeah, so we can switch it off. Yeah, but all the time where we were using GLMnet, this standardization procedure was conducted. You can read more about this in chapter. Which chapter of our textbook, Introduction to Statistical Learning with R? Chapter 6.1, Rich Regression, and there is example called an application to the credit data, and there is 1 or 2 paragraphs about the standardization. Yeah, so this is it. Yeah, so those shrinkage methods are quite successful in selecting variables if we have a lot of competing variables in our model. What is quite problematic is that here everything is linear. Yeah, so LASSO method, LASSO or rich regression, doesn't detect some interaction between the variables or some non-linearities. In practice, we can implement this in shrinkage methods by providing our own interactions as additional variables, interactions, some squared terms or some polynomials. But that being said, is a bit less elegant than in methods that we're gonna discuss in the next part, namely in tree-based models. Yeah, in tree-based models, those non-linearities and interactions are endogenous result of machine learning procedure. Yeah, so I think that this is it for. I guess that's the longest video I recorded for this course. Yeah, and yeah. So have a nice whatever daytime you experience now. Yeah, so see you in the next part. Ciao.